Okay, here is a subsection continuing the discussion on waves, especially waves that propagate in an unbounded region. We cannot compute in unbounded region, so we need to truncate the domain. And in order to truncate the domain without creating artificial reflections, the perfectly meshed layer is a great technique for doing that. So in this tutorial, we're going to see perfectly meshed layer used for source problems and for eigenvalue problems or resonances. So for source problem, the equation is very much the same as what we saw in the previous tutorial. Only the boundary condition has changed. The boundary condition is now an outgoing radiation condition at infinity because the domain is infinite. Okay, so what PML does is to do a transformation that allows you to impose, instead of imposing this non boundary condition at infinity, it allows us to impose a boundary condition in a finite domain. Okay, so we'll see that in a second. First, let's make the geometry. Oh, I forgot to do something. I'm sorry. There. Okay, here's the geometry. It's simpler than before. It's got two circles, and it's got a pulse like before. Here's the pulse. Here's air, a circle of air, and this is an artificial layer where we're going to put this artificial perfectly meshed layer in order to make the solution go down and exponentially decay without creating backward waves. Okay, so the PML facility in NGSolve implements this using a technique that from a paper by Colino and Monk, where is that right, Peter? It's a the complex transformation. That's your thing, right? Oh, okay. Oh, from the previous papers. Okay. So the implementation in NGSolve is there's an object called PML, and you can set a radial PML by providing a strength to the PML, which is sort of the strength of the exponential decay, and a radius of the where the PML region ought to start. With respect to this origin. Okay, once you set this, the mesh gets a complex transformation. So if you want the mesh to behave like an ordinary mesh without the PML, you might not get the expected results. Once you set the PML, the mesh has this transformation built in, and we make the finite element space, and we solve the problem. Here's the Helmholtz problem. You can read off from the bilinear form with this outgoing boundary condition imposed at the end of the PML. The only change is this one line. So you don't see anything. The form hasn't changed. When you look at it, you make the form as if you're solving a problem on this finite domain, but you get a solution like this, which gives you the correct solution on the inside, and on this artificial PML layer, the solution decays exponentially. Okay, so this makes it very convenient to jump into to add a PML without thinking about the complex transformation required to program the PML. Okay, now we can do the same thing for an eigenvalue problem. Yeah, Peter.
What's a good rule for choosing the alpha? Sorry, I put on the spot.
Okay, for resonance problems, very complicated. For source problems, I think maybe you could look at the distance to, what's the strength of the wave at the entry to the PML, and then kind of estimate. I don't know. Maybe you want to say something, Joachim?
frequency dependent quadratic eigenvalue problem as people are doing. I think it's too much now for going into.
No, I
It's a very well, certainly you have more answers than your question was.
Okay, it's a constant struggle. Is my answer.
Yeah, if you're trying to find eigenvalues, you can do a bunch of different alphas, and if you have, say, you know the exact eigenvalue, then you can do plots. I've done various plots of different alphas, and it's like tends to be the case that like after a very small amount of alpha, like you get a good estimate of your eigenvalue, and it's really stable. But then very high is too much. So around 1 or 2 is often perfectly good.
Trial and error, yeah.
But it's ad hoc.
Okay, so we can do the same procedure with setting the PML on this mesh and solve an eigenvalue problem, and that would be a resonance computation. And here is a domain. We argued about the name of this domain. But okay, I didn't want to call it a mushroom, but eventually Joachim won, and we call this a mushroom. But it's not a mushroom. This is air. It's just an opening where the waves enter, and then waves go out, and all of this is air, even though it looks like a mushroom. And outside of this area is going to be the PML. The area of the PML is set. Okay. So we made the domain so that there's a subregion, or there's a subdomain region called PML, and in that region we set the PML just like before, and the remaining steps are very much similar, except I should have noted this. If you want to think of this as an eigenvalue problem, move this omega squared to the other side, and lambda equals omega squared is the eigenvalue that we're going to compute. So it's an eigenvalue of the Laplacian, but it's an eigenvalue of the Laplacian with outgoing strange boundary conditions, so you cannot even expect the eigenvalues to be real. Okay, here is the standard bilinear form of the Laplacian. Here is the standard bilinear form for the mass matrix. What is hidden here is that the mesh already has this complex transformation in the PML. So when I say, yeah, it's a standard Laplacian, well, it's got the Laplacian with the PML in it. Okay. Knowing that, we solve it using an Arnoldi solver for eigenvalues, and it gives you a list of some 50 eigenvalues, I think. And here is a picture of the first one. You see something that looks like a mode that starts off over here and then kind of dissipates in. And this is only one of the 50 modes computed. So if you want to, yeah, okay, I can do that. But let me
Open complex. Complex subfolder.
Okay, and okay, here is the animation, and here is how you get the other components. So this is a grid function with multi-dimensional grid function. So this is one of the modes that was computed by the Arnoldi, and if you want to get the other one, you increase this multi-dimensional component by these are all the different modes that was computed by that Arnoldi solver. And corresponding to each of these modes, there is an eigenvalue or a Ritz value. Let me get out. And you can print all of them right here. And you can see that they are complex, and some of them are interest. Some of them have small imaginary parts, and those are the ones with more confinement, etc., etc. And maybe instead of staring at the numbers, it's nicer to view these things in the complex plane. Here are the eigenvalues, or the omega values, the resonance values that were computed by the Arnoldi solver in the complex plane. Some of them are very close to the real axis, while the others are all below the real axis. Okay, questions?